something on the theory of Lucas.
Yes. Thank you to the organizer for the invitation. So today I want to talk about the theory of Lucas coloring. So let's start with the motivation that why I came up with this definition. So let's start with the okay, all right. So a acidic diamond, AD of n. So its order n is defined as the union of all units squared in the contour absolute value of x plus absolute value of y is equal to n plus 1. For example, the first one is AD of 2, AD of 3, AD of 4, and AD of 5. So one of the very beautiful relationship between the acidic diamond and the ASM is given by Ilkes, Kuperberg, Larsen, and Prop. So what they essentially proved is that the number of domino tiling of AD of n is exactly given by 2 to the power n plus of A, where you are summing over all n by n alternating sign matrices. It is also same as n minus of A, where you are summing over A n plus 1 cross n plus 1 ASMs, where n plus or n minus, it denotes the number of plus 1 or minus 1 in the matrix A. So when I first saw this result, I found it really fascinating. And then last year in 2024, I met Arvind. So I asked him, so do you know any result in the context, or similar kind of result in the context of rhombus tiling or the Logence tiling? And he said that no, he's not aware of any result of this sort, and finding any kind of relationship would be interesting. So there are essentially two challenges associated to this question. One is you need to find an algebraic slot / combinatorial object like ASM, and you want to define a statistics like n plus or n minus like we had earlier. And the second one would be to identify a Logence tiling enumeration problem in the context of, for this particular challenge one, right? You already have the acidic diamond for the domino tiling. So what is the similar kind of problem in the Logence tiling, in the realm of Logence tiling? So these are the two challenges associated to the question. So before I give you the definition of the Lucas coloring, let me give you some example. So essentially, Lucas coloring is an edge coloring. You start with a planar graph. You are coloring each of the edge by two symbol, y or n, and with some stipulation. So first of all, Lucas coloring is a local property. So it should be a property that is defined on each vertex, and we'll come to the definition in a minute. And then, so how do you start basically? You start with a orientation of the plane, whether it is the clockwise orientation or the anti-clockwise orientation. So as soon as you fix the orientation, you will naturally get a cyclic ordering around each vertices on the edges, right? And now the condition is that the n color with this cyclic ordering, which you kind of induced by the orientation, so the n colored edges should appear consecutively. So whenever there is n colored edge, the left hand side or the previous one or the next one has to be another n colored edge. And the second condition is the n colored edges has to be partitioned into pair of consecutive edges. Like for example, if I just look at this picture, the left hand side is an example of Lucas coloring, and the right hand side is not, because there are three edges. Like for example, you can see on the right hand side there are three n colored edges. I simply cannot really partition them into pair of consecutive edges. So that's not an. So let's look at the definition, formal definition. So say Lucas coloring is an edge coloring which satisfies the two condition. So one is that the n colored edges must appear consecutively, and the second one is that whenever they can be partitioned into disjoint collection of size 2 sets consisting of consecutive edges. And the formal definition, in order to define it formally, you need to first fix the orientation of the plane and so on and so forth. You have to then, it induces a cyclic ordering on the edges of each vertex, and then it's a local condition. Okay, so now I have defined the combinatorial object. So let me define few terms associated with the Lucas coloring. So whenever you have a planar graph G, so I'm going to call Luc of G, LUC of G. So that denotes the collection of all Lucas coloring on the graph G. And now if X is a specific Lucas coloring on the graph G, then you are going to call a vertex V a special vertex if all the incident edges are actually colored by N. So there is no Y colored edges, so everything would be colored by N. So then you call it a special vertex. So let's see some example. Like for example, if you look at the triangular graph, you see that there are two possible Lucas coloring, where one is everything is colored by Y and the other one is everything is colored by N. The first coloring, there is no special vertex. However, on the second coloring, there are 3 special vertex. So all the 3 vertices are the special vertex. And there is another example. This graph is called the wheel graph, and apparently it has like 11 Lucas coloring. And of course, one very easy observation is that if you have a special vertex, then it has to be an even, the degree of that vertex has to be even. So in this case, only on the last 2 Lucas coloring, it has a 2 special vertex, which is the where the 2 diagonal intersects, and rest of the vertices are not a special vertex in the Lucas coloring. Okay, so here is a sum we are going to look at. So if G is a planar graph and look of G denotes the collection of all Lucas coloring of the graph G, so then I'm going to look at this particular sum, that you are going to sum over all the possible Lucas coloring, and then you are going to take 2 to the power sp of x. So for each Lucas coloring, you are actually counting how many particular special vertices you have, special points you have, and then you are raising it to the power of 2. And then you are going to sum it over all possible Lucas colorings. So that's the possible sum we are going to look at. Okay, so now I have told you the problem. I have told you the combinatorial object. Now let's come to the second challenge, which is the finding a problem. So we want to find the number of Login styling for this kind of diagrams. Chukwu and Kattenthaler, so they actually investigated the Login styling of this kind of region, which I'm going to call it Tn, in their paper, Enumeration of Login styling of hexagons with cut-off corners. So let me formally define these regions for you. So in general, you can define Tn as you look at the n cross n cube, and then you delete the 3 maximal non-intersecting staircases from its corner. So whatever you are left with, that's your Tn. So in this case, we are looking at T5. So okay, so if you just look at the enumeration, some explicit computations, you see that a lot of large primes kind of appears in this enumeration of the Login styling for this kind of diagrams Tn. So you see that for n is equal to 7, you have 73. For n is equal to 6, you have 127, and which kind of suggests that there probably is not a nice product formula for this specific problem. Okay, so here is the result. So the result says that for each natural number n, so let Tn denotes the configurations which I just described before. So then there exists a collection of planar graph Tn which says that the number of Login styling of Tn is exactly the sum I just mentioned. That's you are summing over all possible Lucas colorings and 2 to the power sp of x, where look of Tn denotes the collection of Lucas coloring and sp of x is the number of special vertex. So let me just tell you what is this graph Tn. So the way the graph Tn is constructed, you start with an equilateral triangle, you put n minus 2 intermediate points in each edge, and you connect the two at the points such that the resulting edge is parallel to the third side. So that, and then you connect all the possible lines. Then Tn, the small tn, is nothing but the resulting triangulation. Like for example, this is T5. So this is the T5. Okay, so let's do a dummy computation. So here is the explicit computation for T3. So these are the 10 possible Lucas coloring for the graph small T3. And for example, if I do the computation, so for example, the first, and so the red vertices are telling you that special vertices. Okay, so for example, in the first graph, there is no special vertex. For the second graph, there is only one special vertex. For the third graph, again, there is one. So I'm just basically adding all of those things, 2 to the power 0 plus 2 to the power 1 ... And I'm indeed getting 104. And if I go back, so let's just try to connect. So you see that it does indeed gives you 2 cube times 13. So which was the intended number which are supposed to get, which is 104. 8 times 33. 8 times 13 for n is equal to 3. Yeah. So, all right. So for the proof is not really difficult. It's a very nice bijective proof exists. So for the rest of the talk, I'm going to focus on the 4 regular planar graph. And this is where the most interesting thing actually happens. So if G is a 4 regular planar graph, so now we see that there are around each vertex that the condition for Lucas coloring tells you there are exactly one of these 6 possible coloring schemes. So if you know FPL model, the fully packed looped models, so the last 4s are very much similar to, it coincides with the fully packed looped models However, the first two is kind of new. And I'm using the conversion scheme that y is going to be converted with green color and the red is going to be converted with the in color. Think of it, you are driving, you are stuck in a traffic. If it is red, then you have to stop. So it is no, you are not allowed to go. If it is green, then you are allowed to go yes. So y will replaced with the green color. So, okay, sorry, it's just not really working. Okay, so apparently, so interestingly enough, you can also retrieve the n cross n alternating sign matrices out of this Lucas coloring. So again, the argument relies on the simple combinatorial argument. So let me tell you how the conversion works. So suppose you start with a 4x4 ASM, and now like the FPL model, so you fix a boundary condition on the grid graph. So what is the grid graph? So GN, the grid graph is nothing but there are n horizontal lines, n vertical lines, and every pair of lines intersect transversally. So you have this grid graph and you are fixing the boundary conditions. And again, you see that the boundary condition is slightly different than the fully packed loop models. So there the boundary condition is alternating. So red, for example, this adjacent horizontal, the vertical line should also be green. So here the horizontal and the vertical boundaries that should have the same color. And now how is the conversion works? So for example, I will read each row and then I will read each column. So for example, and if you have 0, then you change the color. If you have non-zero element, then you don't change the color. Like for example, I have 0, and then I'm just looking at the first row, the first line, the first horizontal line. So if it is 0, then I'm changing the color from red to green. If it is 1, I don't change the color. I will keep the red as it is. Then 0, then green becomes red, and 0, then it will automatically be taken care of by the boundary. So similarly with the second row as well. So 1 minus 1, 1. You see that the color doesn't change here. So all the color remains same. And there is a 0, and then it automatically takes care by the boundary condition there. And similarly, you do the coloring on the column wise. You read the matrices column wise. You extend the color column wise, and that's what the resulting picture tells you. And then in the opposite direction, it's very simple because of this. I told you how to convert this. So you know where to put the zeros. So you put the zeros from this coloring scheme when you want to construct the matrix. And then when you put the zeros and you know where the non-zero entry is gonna go. So you then put 1 minus 1 alternatively, and that will actually give you the corresponding matrix in the opposite direction. Okay, so now I want to connect the story with something called the Khovanov homology. So I want to bring the topology side as well. So many of you may not know what Jones polynomial is. Here is a quick introduction. So if you start with a link diagram, so von Jones actually defined a Laurent polynomial. So Laurent polynomial in Z, Q, and Q inverse, and the polynomial is called the Jones polynomial, and it is a topological invariant in the sense that if you change the diagram by Reidemeister 1, 2, or 3 moves, you end up getting the same polynomial. So this is a very famous polynomial called the Jones polynomial. So, and then came Khovanov. So what Khovanov did actually, so Khovanov categorified the Jones polynomial. So what he did actually, he constructed a chain complex, a bigraded chain complex, which I'm going to call CKH of D with the differential DKH. And the gradings are bigraded. It's a Z cross Z grading. And now if you look at the graded Euler characteristic, that actually retrieves the Jones polynomial. Okay, there are too much complication. Let me show you with some example. So what is it showing is that this is how the Khovanov complex is going to look like. It's a direct sum of chain complexes, right? So and those arrows are pointing the differentials, right? And now for each arrow, you are going to look at the Euler characteristic as the graded sum, negative alternating sum of the rank of the homology, right? And now we are going to track like exactly which height it occurs. So that's what, if you just go back. So, okay, if I just go back, so it's like the normal graded Euler characteristic, and then I'm going to track it exactly which height it appears, q to the power j, and you are summing over I comma j, and that exactly gives you the Jones polynomial. So that's the Jones polynomial for you. Okay. So now, so that's how the story actually ends. So Yeo-Sun Lee, so she actually introduced a map phi. It's a kind of a mysterious maps in the Khovanov complex, which satisfies the condition that phi square is equal to 0. And then if you combine DKH composed with phi plus phi composed DKH, that should be 0. Again, let me give you a schematic picture. So here is as before I have the Khovanov picture. and these blue arrows are indicating the Lie differential, the phi map. So what is the condition phi square is equal to 0 is telling you? So if I just go back, so phi square is equal to 0 means that if I just, if I just compose, if I just go along this blue arrow, so that is also differential. That means that phi square is equal to 0. And the second condition is telling you, so if I just go back, so dkh compose phi plus phi compose dkh is equal to 0. So the way you should interpret this, whenever I have a parallelogram, so then that resulted things, like for example, I can look at this parallelogram. So phi compose dkh plus phi compose another dkh, so the result should be 0. Okay, so that's what it is. So basically, so let me just write down here. So I know that dkh squared is equal to 0 because that's a Komarov differential. And now if I look at dkh plus phi squared, so that gives you dkh squared plus dkh compose phi plus phi compose dkh plus phi squared is equal to 0. So this terms is equal to 0 because that's a Komarov differential. So these terms are the additional terms which was proven by Lie. So she showed that these terms are also 0. So now that means that this forms a new differential. So this is called a perturbation. So instead of looking at the homology with respect to dkh, we can look at this part-up differential. So and what is the interesting theorem is that, so if D is a k component link diagram, so then the total homology of this part-up differential, so we were adding this phi on the Komarov differential, so it has the total dimension is exactly is equal to 2 to the power k, where k being the number of link component. Okay, so that's a very interesting, and also just one point, that's when Professor Krattenthaler was showing the slides in the morning, and Rod Barnaton's name also came in the list of people who actually verified the proof, Zeilberger's proof, and Rod Barnaton was also there, so which was really interesting. Okay, so one thing, so although Lie's proof of this theorem is quite computational, however, the way Rod Barnaton and the Scott Morrison, they gave a very elegant and the conceptually nice proof, and they uses some very geometric idea called the Karoubi envelope and of the cobordism category. Again, whatever that is, we can ignore. But now let me interpret. So we have been talking about Lucas coloring. So let me interpret how to understand that particular theorem with this language we developed called the Lucas coloring. So here is the interpretation, the reinterpretation of the theorem using our language. So you start with a 4 regular planar graph and d tilde. So this is the same, it's a link diagram which you construct out of d by you get rid of the vertex v and then you just add a crossing. Okay, like for example, locally, if you have a picture like this, then just add a diagram. You just add a crossing. It doesn't matter whether it is an over crossing or under crossing. You just add a crossing, because if you look at that, remember the theorem, it says that the total homology is exactly 2 to the power number of link component, and the number of link component remains same if I change the over crossing with under crossing. So the link component, the connected component has to be same. Okay, so and now you have the d tilde is the link diagram, which you do this operation for each vertex, and then you have a link diagram. Excuse me. And now I'm going to look at the sub-collection of the collection of all Lucas coloring, such that around each vertex, it has to be colored by one of these 4 coloring schemes. So these are the common scheme for the FPL fully packed looped models as well. So for around each vertex, it has to be one of this coloring scheme. So then what is the theorem, what is the reinterpretation of the theorem is, it says that this new sub-collection, the cardinality of this is exactly 2 to the power number of link component. Let's see some example. So suppose let's look at this particular diagram. So the first one is some kind of it's a 4-valent planar graph. It's a 4 regular planar graph, and that's the d tilde. I have added some crossing. Again, doesn't matter whether it is over crossing or under crossing. And now you see that the number of link component is exactly 2. And this theorem tells you, if I have this condition around each of these 4 vertex, and there are precisely 4 Lucas coloring, and which is the matches with the result. So the number of Lucas coloring in this case is exactly 4 in this case, and it is also 2 to the power number of link component, which is 2 squared exactly is equal to 4. Okay, so now I want to give you a closed formula. So if you start with a planar graph, four regular planar graph, how to find a closed formula for the Lucas coloring, the number of Lucas coloring. So here is, although it's not a planar nice product formula, but it's like more like a sum formula. So let me tell you what is happening actually. So you start with a four regular planar graph, and for around each vertex locally, you change the vertex either by two smoothing, left smoothing or right smoothing, or you add one crossing. Again, doesn't matter whether it is over crossing or under crossing. So now if I do it for each of the vertex of the graph of the four regular planar graph, then essentially you will get 3 to the power k many different link diagram, where k being the number of vertices. If I do it for each vertex, so then every time, so it will essentially produces 3 different branching. So then it will essentially give you 3 to the power k many different link diagrams. So what is the formula? So the formula is the following. So the enumeration of the Lucas coloring is exactly given by 1 over 2 to the power k, and you are summing over that thing, the 2 to the power number of link components t. So you look at this particular sub collection which has 3 to the power k many elements. For each link diagram, I'm going to see how many link components are there, and then I'm going to take the statistics to the 2 to the power number of link components, adding them up and dividing it by 2 to the power k. And that's exactly gives you the number of Lucas coloring of the graph. So let me give you a proof, because a math talk is always incomplete without one proof. And this proof is just a picture. So I can actually tell you how to understand this. So first step is that, so you start with a Lucas coloring. So now locally, I want to get rid of the vertex by adding the edges which are of the same color. Okay. So like for example, if I have this first coloring scheme, I want to get rid of the vertex by taking that particular smoothing, which is defined by the same red color on the top and the green color on the bottom. Similarly, I do it for the second picture. However, this picture, the last two, I have two different choices, right? So I can either took the left hand side smoothing, or the right hand side smoothing. Again, you just choose one of them, right? So it doesn't matter which one you choose. So now, if I just unravel the Barnatton and the Morrison's result, so what it gives rise to? It gives rise to something called the skein relation. So I'll explain that how to interpret this relation. So the first one, if you see a uncolored edge, so that is going to be same as a red color edge plus green color edge, because any edge, there are two possible colors you can have, either a red color or you can have a green color. So similarly, if I have two parallel uncolored edge, then I will have a 4 different colors, right? So red, green, green, red, and then finally the green, red. So then it's a formal sum. So R square is equal to R. It basically means that I can glue the monochromatic edges. If both of the edges are of the same color, I can glue them. Similarly, G square is equal to G. That's what it is saying. So R plus G is equal to 1. That is the same condition, the first one, that any uncolored edge gets the two color, red and green. So that's what corresponds to algebraically into R plus G is equal to 1. And finally, R times G is equal to G times R is equal to 0. That corresponds to saying that if two colors are if the color doesn't match, then it doesn't give you any proper coloring, right? So if the colors are incompatible, so then they basically vanishes. They just become 0. So that's what RG times is equal to GR is equal to 0 is telling you. Okay, so now if I just follow along the Barnatton's proof, so it gives you this skein relation. First of all, the overcrossing is equal to undercrossing. Because why? Because the theorem just only concerns about number of link component, and the number of link components remains invariant if I change by overcrossing by undercrossing. It doesn't really matter. So then if I just look at the crossing around each crossing, so then it should give you one of these 4 smoothing, basically. So for each crossing, that should be interpreted into some of these 4 possible smoothing. And then the top one, it gives you again the 4 possible coloring. Similarly, the second one also gives you 4 possible coloring. If I add them up, so if I add this relation and along with second and third, you can see that each of them appears exactly twice. So that's the 6. So 4 plus 4 plus 4, there are 12 coloring. You are dividing it by half. That gives you 6 possible colorings. So that means the skein relation is equal to half times adding a smoothing or two different smoothing, adding a crossing or two different smoothing, and you are doing it for each vertex. Then you have k many vertex, for example. That's how you get 1 by 2 to the power k times the number of link components around each vertex. Okay, that's all I have. Thank you for listening. And yeah, and although